Hello, honors pre-calculus students. This is Mr. Hazelhorst coming to you live from room A08 at Papillion La Vista South High School. Wanted to take a few moments here and just share with you guys some information about greatest integer functions and piecewise functions. So sit back and enjoy the show here. Let's begin with the greatest integer function. It's also known as a step function. You're going to see why when we take a moment and graph it here. But we want to start out a little bit with recognizing the notation that signifies a greatest integer function. And it's these kind of combination. It almost looks like the child of a bracket and an absolute, or double absolute values. But that's what we use to represent the greatest integer. All right. So when we say the greatest integer, it's any integer. All right, so thinking positive and negative whole numbers that are less than or equal to whatever number we plug into that greatest integer function notation. So what I always like to think is, I always like to think round down. All right, so let's look at a couple of examples here. We've got 3 examples of greatest integer function that we're going to evaluate. All right, what would the greatest integer of 4 be? All right, well, if we think of 4 is already an integer. And we can't have another integer that's greater than or equal to 4. So in the greatest integer function of 4, that value is 4. Okay. Now the next example we picked, very, very close to 4, like 3.9 repeated, right? That's about as close to 4 as we can get without actually being 4. And if we want to find the greatest integer of 4, all right, the greatest integer that is in this problem is 3. Okay? Now you might think, well, 3.9 repeated is really close to 4, right? But we're looking for the greatest integer that is less than or equal to x. So x is being represented by 3.9 repeated. So our greatest integer here is 3. We get to our next example, all right? Again, first thing we need to do, order of operations, we always need to work within those grouping symbols. And our greatest integer function is like a grouping symbol. We can think of it like a parenthesis or a bracket or braces or absolute value or whatever you want there. So within the grouping symbol, the greatest integer that exists in the number 9.2 is 9. So what this really turns into is 2 times 9. So our greatest integer here would be 18 when we evaluate that expression. Okay? All right, so now that you've kind of seen how we find a greatest integer, let's take a look at what it would look like if we were to graph it. So we're just going to start with the parent function of a greatest integer function. So if I wanted to graph the function f of x equal to the greatest integer of x, all right, again, we need to think through what, as we plug in input values for x, right, what is that graph going to begin to look like, okay? And so let's just kind of break it down here. We'll go back to the basics. When you first learn to graph, we have a tendency to learn how to graph using a table of values. And so let's do that here real quick, all right? So let's input some values for x and evaluate what the function would be at those input values, all right? So let's start out with the number 1, all right? Well, the greatest integer that exists in 1 is 1. Now, since we're dealing with a step function or greatest integer function, we want to deal with some decimal values here. So what if we went 1.1? What would the greatest integer be there? Well, again, it'd be 1. Right? How about like 1.6? Well, again, it's 1. 1.9? Well, it's 1. 2. Well, its greatest integer is 2, right? We could follow the same pattern, all right? So we can see here as we begin to evaluate this function, this is where it also gets its name, a step function. So if I were to graph this, all right, just plotting these points, all right? So let's call this 1. All right, we'll label a scale on my graph here. So we're going to let each square, 2 squares represent 1 unit on my graph. So if I input 1 for x, right, we get 1. If I input 1.1, I get 1. If I input 1.6, I get 1. If I input 1.9, I get 1. All right, so if we connect these dots, what happens is we have this graph that exists, but once I hit 2, right, so I go up 2, but I can't quite get to 2, we create this step. Because once I get to 2, the function steps up, right? So then it exists. Let's follow my scale here. Apologize there. All right, so I create this step, and then again at 2, I step up. And then again at 3, I step up. And at 4, I step up. And the same thing going the other way. All right, 0's greatest integer, right, would be everything that exists from 0 up to, but not including 1. And the same thing with -1, right? -1's greatest integer would be all values up to, but not including 0. And again, we could continue on this pattern, and what we see existing then is this step function. And this is why we also refer to the greatest integer function as a step function. We create this set of steps. All right? So that's an example of a greatest integer function. And that's some notation that we want to recognize and know how to evaluate. So now let's talk about a piecewise function. Piecewise functions, I kind of like to think of them as the Frankensteins of graphs. All right? A piecewise function, by definition, is a set of functions where each separate function covers a separate and specified part of the domain. All right, so a piecewise function, where this idea of Frankenstein comes from, right? Like Frankenstein was put together with lots of different body parts from different people, and then they created this monster that was alive, right? Well, a piecewise function is kind of that same idea. We're going to take different pieces of different graphs, and we're going to put them together to make one complete function. And so if you take a look at our piecewise function here, you notice that we still use the function notation f of x. All right, but when we get to the other side of our equal sign here, this is where it begins to look unique. We have this single brace that is connecting these two functions together. And the first and most important thing we need to recognize is that where are these functions going to exist? And so when I look at the top line of my function, it's going to exist anytime we input a value of x that is less than or equal to a -2. All right, so basically anything that's on the left side of a -2. That's where this function will exist. If I look at my other function, it's going to exist only when x is greater than a -2. So essentially what we're doing is we're taking two parts of these graphs and we're going to put them together to make one complete function. And these are pretty simple to graph. All right, what I'm going to recommend you start with, again, is recognizing, where are these graphs kind of being put together at. And in this example, they're being put together at a -2. Okay, so I want to recognize where -2 is on my graph. All right, so let's just go by single units this time. All right, so this would be -2 on my graph. And so this is kind of the dividing line. All right, so I'm just going to draw for our reference here, just so we can kind of visualize it. This is where the graphs can get joined together, okay? So again, on the left side of this kind of green dotted line, we're going to have the top function. And on the right side of that green dotted line, we're going to have the bottom function. And now I just need to graph each of these separately. All right, so if we begin with the function at -1/2 x plus 2, all right, so normally graphing a line, right, we're going to go up 2, and then I'm going to go down 1 over 2. I'm taking that back. We're going to go up 1 over 2. We're going to make this look like a negative graph here. All right. Now, notice that I used a closed circle. All right. And the reason for that, when I look at the specified domain of this function, recognize that it's less than or equal to. Okay, so as I'm graphing this first function, this point is actually going to be included in the graph. All right, then we'll continue our pattern so that we can make some dots to connect here. All right, and then we're going to draw our function. And notice that I am only drawing it to the left side because, again, that's where this part of the function exists. And then let's jump to our other side here. All right, so we got the function x minus 3. So my y-intercept's at a -3. My slope would be up 1 over 1. Now I need to start back here at -2. So I'm going to begin my graph here with an open circle. Again, because this graph only exists at values greater than a -2. And then we'll draw in our line over the specified domain. And so that gives you an example of what a piecewise function looks like. All right, that's the complete picture of the graph. Well, thank you guys for your time. I just want to encourage you, if you want some more examples and a little more practice, if you go to larsonprecalculus.com under the Solutions tab, you can select Chapter 1, Section 6, and if you view examples 2 and 3, you'll get some more practice with greatest integer functions and piecewise functions. Everybody have a great day, and we'll see you soon.